number one. What is the restoring force on a spring, and where is equilibrium position located? So the restoring force is going to be caused by the spring itself. So the spring itself causes the restoring force. And that's because the spring has a natural kind of tension in itself. And so anything that stretches it out or compresses it, it wants to get back to that natural tension. And equilibrium is the location of the natural tension of the spring. Now, we're going to be dealing with vertical springs. That's what you did the lab on. That's all the things we're going to do. We're going to do vertical springs. So the spring is hanging down, and it's got mass on it. So when there's no mass, it's going to have some natural position it's going to be at. That's the equilibrium point. But that equilibrium point changes when you put mass on it, and that's because the force of gravity will pull down, and the tension in the spring will pull up. And that balance point would be where equilibrium is. So wherever that kind of natural tension is, wherever that balance point is, that's where equilibrium is going to be. Okay. We did a lab. You just finished. So hopefully you'll remember some of these. But what did we say of the following things? So did spring constant have an effect? I got to know. We got to know. Yes, this is an effect on spring constant. So spring constant did have an effect, and it was inversely proportional. So what that means is when you increase the spring constant, the period went down. In other words, it went faster. Okay. So this one's pretty easy to explain. Spring constant is part of the restoring force. So a larger spring constant is going to have more restoring force. So a larger spring constant is going to be more restoring force. And the equation for that is just the F equals negative kx we've seen before. So obviously, if you make k bigger, you're going to make F bigger. So if you make F bigger, it's going to move faster. So larger spring constant means smaller period. It'll take less time. Okay? What about mass? Did mass have an effect? Yes, and that one was directly proportional. So mass did matter, unlike the pendulum where mass did not matter. So on the pendulum, we said mass did not matter because when we increased the mass, gravity didn't. So gravity has the same effect on all objects, is what we said. Why is that not the case here? Why? So it could. So part of it is we're talking about up and down springs, which is affected by gravity, but springs can go side to side, which are not affected by gravity. So springs. Gravity is not a factor in this one. So that means that if you increase the mass, you increase its inertia, but you don't increase the force. See, on pendulums, when you increase the mass, you increase the inertia, but you did increase the force because gravity pulled on it more. Okay? And so because gravity pulled on it more, you had a larger effect. This does not do that. Gravity does not pull on it more. Therefore, more mass means more inertia, which means it's harder to move. So more mass is harder to move. So, and that's because of inertia. Okay? Okay, cruising. Amplitude or displacement. Did amplitude matter? No, that one did not. That one did not. Why not? Why didn't amplitude matter? Why would amplitude not have an effect here? Give me a hint. It's similar to pendulums, if you can remember back that far. Bless you. Yeah, it's going to go faster. Why? Why would it go faster? Has more. Nope. Starts with an E. Has more energy. So the reason why amplitude has no effect is because it has more energy. When you pull it back further, you get it more energy on a pendulum. When you compress it more, you give it more energy on a spring. So I'll say energy is increased to make up for larger differences. Or, sorry, distances. There we go. All right, last one here. We did not test gravity. The reason we didn't test gravity is because it's hard to test gravity. And because, two, gravity has no effect. So gravity is not responsible for the motion of a pendulum. Now, gravity is a force, but what gravity does is it stretches out the spring initially, and then from there the spring behaves as it would on its own. It's not affected by gravity anymore. So if you took a spring up in space, it would behave the exact same up in space as it does here. Okay? You could stretch it out, you could bounce it up and down, it would behave the exact same way up in space. Assuming that you had room for it to oscillate. It would behave the exact same way up in space. So gravity is not a factor. All gravity does is stretch it out to change the equilibrium. So gravity changes equilibrium but not how the spring behaves. Which is what the period is, right? The period is how it's behaving, how it acts. Good. For the pendulum lab, we discussed how its speed and acceleration, restoring force, change during an oscillation. Do those properties behave similarly or differently for a spring? So what we said for a pendulum is you had 5 positions. Okay, so the pendulum went from one side to the other. We said that the velocity was 0 at the amplitude points. We said the velocity was max at the equilibrium. And we said that as it went towards equilibrium, the velocity goes up, and as it goes away from equilibrium, the velocity goes down. Turns out springs behave exactly the same way. Springs behave the same way. So if you have a spring and it starts its motion compressed, okay, that would be the maximum amplitude point. That would be a velocity of 0. Then it's going to stretch out a little bit. At that point, the velocity is increasing. It's getting faster. Then it gets to equilibrium. At that point, it's the fastest it can go. So that's the equilibrium position. Then it keeps going past that point. At that point, it starts to slow down. And then it gets as far as it can go on the other side. And at that point, the velocity is 0 again.
Wait, where's max?
Right at equilibrium.
But I thought equilibrium is when it's at its lowest.
No, so equilibrium is the balance point. So when you lift it up above equilibrium, it'll go down to equilibrium, go below equilibrium, and then go back again. So equilibrium is the fastest point. The other 2 points are at 0. So as you go down on the spring, it'll go from 0, speed up, max, slow down, 0 again. And then it would do the reverse on the way back up again. Okay.